So yeah, I feel pretty good. My kids have to get up for school anyway, so it was like perfect timing. So yeah, it was.
Oh.
So, Tali, you want to let people in? It's about a few minutes.
We have 3 minutes. Yeah, I give it another 2
Yeah.
and then I will admit everyone.
And Jesse, just to remind you, when Telly admits everyone, everyone's monitor will go off and everyone will be muted. So we'll have to turn ours back on and unmute ourselves.
Okay.
So, Jesse, try to use the pointer if you can.
Yeah, we'll do.
And Bala, did you want to say anything before I introduce Jesse, or do you want me to introduce him right away?
No, now that we are, yeah, you could.
Okay.
Yeah. So you don't go to AICHE, Ted?
I do sometimes. I used to go almost every year, but it was always challenge going to AICHE and APS or ASME, and it just got really difficult.
Yeah. And there is no virtual option.
I don't even know.
Okay.
And you know, if when you're teaching in the fall, it's also hard to go, you know, for a whole week.
Yeah.
Yeah. There's always a decent like fluidization session.
Yes. Yeah. And there's also several pharmaceutical companies or particulate companies, Dow, ExxonMobil, that do fluidized beds.
Yeah.
Yeah.
Okay, I'm gonna admit people in.
Okay.
We will get started in a few minutes. So Jesse, maybe if you'd like to share your screen and then I'll get started.
Yeah, sure.
So welcome, good morning, good afternoon, good evening, wherever you're located on this earth. My name is Ted Heindel. I'm with Iowa State University, and it's my pleasure to introduce our speaker today. Our speaker comes from University of Michigan in Department of Mechanical and Aerospace Engineering. Jesse Capecelatro joined University of Michigan in 2016. Before that, he was a postdoc at University of Illinois, Urbana-Champaign, where he started his activities in compressible fluid flow. He received his PhD from Cornell University working on particulate systems, particularly in fluidized beds. So that's where he started his particulate activity. And his research is broadly under the realm of fluid mechanics with this emphasis on particle-laden flows, turbulence, reacting flows, and high-performance computing. He has applications in renewable energy, propulsion, disease transmission, and space exploration. And today he's going to talk to us about particle or gas particle dynamics in high-speed flows, insights from 18th century cannon firing to particle resolve simulations. So Jesse, the floor is yours.
All right, great. Yeah, thank you for inviting me to give this talk. And yeah, I think, I decided instead of just sort of summarizing some of the work that my group's done over the last couple of years, I wanted to provide sort of some historical context and lay the groundwork. And the more sort of I learned about some of the sort of the origins of some of the models that we use today, et cetera, kind of the more fascinating I found it to be. And so the first part of this talk, or a bit of this talk, will be on sort of some interesting, what I find to be some interesting history. And then I'll show some of the work we've done in the latter half. And, as Ted mentioned, my PhD was on particle-laden flows. My postdoc was on compressible flows. And since joining Michigan, I've been sort of combining those areas. And it's been a learning process as I've been working in this area. And so I hope to share some of, what I've learned over the last couple of years and show some of the work my group's been doing. Just real quick. So my group, we're located in Ann Arbor, and here's pictures of some of my current and former students and postdocs. And a lot of the work I'm showing today was really started by my former PhD student, Greg Shallcross, who's now at JPL. And I'll be showing work also from my former postdoc, who's now at Mehdi, who's now at Dow Chemical, and two of my current students, Meet and Archana. So most of the work I'm showing has been they've been driving those efforts. And I guess before we begin, I'd like to get a show of hands real quick. I guess I don't know how to see the chat right now. So instead, I presume that many folks here have background in CFD, numerical methods. And if you're like me, you've come across the Adams-Bashforth method. And if you're like me, you've never really questioned, who Adams or Bashforth were. And so if nothing else, by the end of this talk, I hope that you'll have a better understanding of who those folks were, and some interesting background of how they ended up developing this numerical time integration method. So we'll get to that in like a couple of slides. So just keep that in the back of your mind. So a lot of the work I'm showing today was funded by NASA, and they're particularly interested or concerned with the interaction of high-speed exhausts or jets during powered descent of a spacecraft interacting with the surface of a planet or the moon. And so this is what NASA calls plume surface interactions. And the reason this is a concern is because when a spacecraft is approaching the surface of a planet, the high-speed jet erodes the surface. If you're in a low atmosphere environment, there's not a lot of drag to slow those particles down. And so once they start moving, there's not a lot to slow them down, and they can really get to very high speeds. And the jet can form craters, and that could lead to stability issues with the lander. And we're at this point where NASA's been quite successful, right, in landing on with the previous lunar missions and Mars missions. But it's important to remind ourselves that 4 of the 6 Apollo landings suffered from hindered visibility due to plume surface interactions. And just to give an idea of one of these examples, this is an image of the Apollo 12 lander. And about 160 meters from the lander was the Surveyor 3. So this was a former mission that was on the surface. And the plan was to return some of the equipment in this mission. And during landing, there was so much erosion of the lunar dust and high-speed ejection of the lunar dust that a lot of the equipment ended up getting essentially sandblasted. And this is, so landing doesn't only jeopardize the lander itself, but also surrounding equipment. This is an image showing during the Apollo 12 landing some of the dust that was being injected. And it was actually estimated that the dust was traveling upwards of 100 meters per second. And it's believed that some of the dust reached orbital speeds. And so there's dust currently orbiting the moon and depositing on satellites that was ejected during a landing event. So it's a real issue, especially on the moon. Now, with some of the previous Mars landings, they tried to avoid this issue by introducing the sky crane maneuver. So the idea is the sky crane comes in and hovers at about 30 feet above the surface or 10 meters to prevent the exhaust plumes from getting too close to the surface, and then they lower the lander. And this works fairly well, but still on the Martian environment, you could see that there's still very large craters that are formed during landing. You could see from one of the cameras from the InSight spacecraft, there's still loss of visibility. And it's believed that one of the wind sensors of the Curiosity rover might have been damaged due to rocks that were ejected during the sky crane maneuver. So even preventing the exhaust plumes from getting really close to the surface, you still get significant erosion, cratering, and soil and rocks being ejected. And with future missions of crewed missions sending people to Mars or sample return taking off from the surface, these problems are only going to be greater. And so this is a challenge that's really going to potentially affect every future mission. And there's a lot that's unknown, and it's difficult to design in these extreme environments. So as a fluid dynamicist, I like to think of what are the relevant non-dimensional numbers. So this is a sketch of a supersonic jet impinging on a surface, and you can see that in the surface of the planet, the soil is at around closed packing, so very high volume fractions. As you move up, the volume fraction decreases until you get to very dilute ejecta up here. You have Mach numbers that range from supersonic. The flow gets deflected, and so you have a region, this plate shock here. We have strong recirculation and turbulence where the flow is subsonic, but when the flow gets deflected, it accelerates. And in this viscous erosion region, accelerates to supersonic speeds. So you have this combination of high speed, high Mach number flows to turbulent subsonic flows across the whole span of volume fractions. Even in low atmosphere environments like the moon, within the plume and within this sort of stagnation shock, the density is high enough that we can treat the flow as continuum. So those of us who prefer to solve the Navier-Stokes equations, that's a comfort. But obviously, in some of those environments, you have continuum to rarefied sort of transition. And so this is a very difficult multi-phase flow. As I said, it spans dilute to dense loadings, subsonic to supersonic, and continuum rarefied. So take for someone like myself who is trained in particle-laden flows in the incompressible limits, you take all of those challenges and you amplify it by orders of magnitude when you go into these extreme conditions. Now, high-speed gas particle flows are not only relevant to space exploration, but a whole range of different disciplines across science and engineering. So volcanic eruptions are characterized by compressible flows and a range of particle sizes and volume fractions, coal dust explosions, and detonation of heterogeneous materials. These are all other examples where you have a compressible flow that's made up of particles. And that's really the focus of today's talk. So the plan I have for the next 40 minutes is to begin with some of the equations of motion and sort of highlight what do we know, what don't we know. If we want to arrive at a coarse grain model, what are some of the subgrid sort of terms that we need to focus on, and that'll lead into this idea that the drag force is one of the biggest or most important terms. And so following that, I'll talk about some of the origins of modern day drag laws. And this is where, Adams and Bashforth will play a role. And so keep that in mind. And then I'll show some work that my group's done developing new drag laws, looking at doing turbulence modeling in these extreme conditions. And then in the last 5 minutes, I'd like to show some sort of ongoing work where we're bringing this all together and returning to this plume surface interaction problem. So that's today's plan. So, again, my background was in incompressible particle-laden flows. And so I always, when I think about these types of flow conditions, I always make it in comparison to the incompressible limit. And if we begin with just some of the scales of motion, so for incompressible flow, some of the important length scales, you have the boundary layer thickness on the surface of the particle. The flow is turbulent. The Kolmogorov length scale and time scale comes into play. Obviously, the particle diameter is important length scale. And then, the particle response time due to drag is one of the main time scales. Now, for compressible flow, when particles start moving at high speeds, you have the emergence of a bow shock. And so shock waves have very small thicknesses on the order of angstroms, right? So much smaller than the particle diameter. And then the acoustic time scale. So the amount of time it takes for a disturbance to travel at the speed of sound is typically much faster than the particle response time due to drag. And just as an example, if you imagine a grain of sand, 100 micron particle density of 3,000 in air, that drag response time is going to be on the order of 0.1 seconds. But the acoustic time scale, so the time it takes for the disturbance to travel at the speed of sound over the length of the particle diameter, is many orders of magnitude smaller than that. And so this introduces a lot of challenges if we want to do numerical simulations or experimental measurements, just because we have this a much wider range of scales at play. And so what I'd like to do is just show at least an approach we're taking to sort of arrive at a coarse grain type of models. And to begin, we're going to consider we have two phases and the interface is known. So we have, we can define an indicator function that's 1 inside the fluid, 0 inside the particle. And we can introduce the volume occupied by the particle and the fluid respectively. And the idea is we want to arrive at a set of equations where we don't have to resolve at a subparticle scale sort of resolution, right? Because that's just going to be impractical for most cases. We want to arrive at some type of either two fluid model or Euler-Lagrange type of approach that allows us to start to look at problem sizes of interest and solve the relevant equations. And so the approach we typically take is to introduce a filter. So you could think of this as a Gaussian that's going to has some length scale delta F that's bigger than the particle. And if we integrate that Gaussian or take the convolution with some quantity, some microscale quantity, and multiply it by the indicator function, we end up with a volume fraction times a filtered field. So this is analogous to large eddy simulation. The main difference is in LES, your filter is not truncated by the indicator function. And so because we have the particles present, the filter is truncated, and we're going to arrive at surface contributions in terms that would not typically arise in single phase LES. A couple of constraints on the filter. We want the filter bigger than the particle so we can solve for our, say, gas phase quantities on a resolution larger than the particle, but it should be smaller than some macroscopic length scale so that we can resolve the relevant sort of mesoscale features in the flow. And we require that the grid spacing is smaller than the filter so that the equations are properly resolved. Now, this is not new, right? So there were a number of attempts in the early 60s to arrive at a coarse grain set of equations using like control volume analyses and introducing source terms in sort of an ad hoc manner. But it was Anderson and Jackson in 1967 who basically formulated these equations for an arbitrary filter, and many of the two fluid models and Euler-Lagrange simulations we use today solve equations that are based on this formulation. They did this for incompressible flow, and my student Greg has an IJMF paper where he extended this for the compressible flow equations, which I want to briefly highlight in the next couple of slides, with the purpose of just showing, unlike in incompressible flows, some of the new unclosed terms that arise. So if we start with the compressible Navier-Stokes equations, again, so we're starting with this implicit assumption that we can treat the flow as continuum. Again, for many applications that's relevant, but you always have to be mindful of what the Knudsen numbers are if you're looking at compressible particle flows, because that might not always be the case. But starting with the continuum assumption, applying this volume filter, conservation of mass looks very similar to the single phase case, but now we have a volume fraction appearing. And filtering the momentum equation, we have the surface contribution. So we have the fluid stress at the subfilter scale integrated on the surface of each particle. This is exactly what we would call drag and lift, right? So this is where all of the hydrodynamic interactions acting on the particles would come into play. And because we're not resolving the flow at the subparticle level, this term requires models, right? Another unclosed term is filtering the convective, nonlinear convective term. You end up with a Reynolds stress-like term. The main difference compared to single-phase flows is that here we have velocity fluctuations that can originate at the scale of individual particles. So you have wakes shed by individual particles that can lead to velocity fluctuations that would not exist if the particles weren't there. So this is unlike the typical energy cascade. We have large scale motion cascade to small scales. Here you have velocity being produced at the smallest scales. And this is just an example that even in a laminar flow, if you have a wake that's shed past a particle and your filter is bigger than that particle, you can have this velocity variation. So even in laminar flow, you can have a nonlinear Reynolds stress-like term. So we typically call this a pseudo-turbulent Reynolds stress instead of the typical Reynolds stress. But this, again, like I said, people have been solving these equations for a number of years. When we now turn to the energy equation, because we're interested in compressible flows, we have a lot of new terms that I'm showing in red that appear. So namely, this Q is due to interface heat exchange. And so usually this is modeled with like a Nusselt number correlation. Again, that Reynolds stress term appears not only in momentum, but in a number of places in the energy equation. So if we consider the thermodynamic relation that relates to the total energy with pressure, the Reynolds stress acts to systematically reduce the pressure and consequently the local sound speed. And this has a consequence, an increase in local Mach number. So the Reynolds stress plays a role in the equation of states. This is just showing an example of a 2D calculation, and we'll come back at the end of this talk and look at this flow in more detail. But you can see here the color is the velocity field, and all of the velocity fluctuations here are induced by the presence of the particles. So this is what we mean by the Reynolds stress. And you can see that the flow chokes at the downstream region and accelerates to supersonic speed. So the particles here act as sort of like create a nozzling effect that can choke the flow. And so the two-way coupling is fundamentally different, compared to what you'd have in incompressible flow due to this compressible phenomena. Now, there's a number of unclosed terms that appear in this divergence, and through looking at particle resolved calculations, we see that a number of them are either negligible or can be rewritten in terms of other terms. And so the main story here is if we want to solve the volume filtered or locally averaged compressible flow equations, the two main unclosed terms are the Reynolds stress and the drag. So we see that we have work due to drag in the energy equation. I'm not going to talk much about the heat exchange term here. So we'll assume that we have accurate Nusselt number correlations, but again, this can be revisited as well. So if we turn our attention to the particles, if we think about the forces acting on an individual particle, there's the fluid stress, so the viscous and pressure acting on the surface. So this is where drag and lift would appear, and then any external forces due to, say, gravity or collisions. And the BBO equations, or extended by Maxey-Riley, typically decompose the forces into quasi-steady drag and unsteady contributions due to inviscid unsteady terms due to added mass, viscous unsteady due to Basse history. Kind of the last 10 years or so, there's been a number of contributions from Bala's group. So Palmer has a nice physical review letters paper in JFM where they extend these equations to compressible flows, albeit in the limit of zero Reynolds number and Mach number. And so this provides a framework to start, looking at the forces acting on the particles, but they'll require, sort of empirical extensions, for example, using like a drag coefficient to apply them in finite Reynolds number, Mach number flows. And, one of the interesting things here is when we talk about gas solid flows where the particle density is much greater than the gas, we typically neglect these unsteady contributions. So this unsteady term due to the undisturbed flow, this is typically due to the pressure gradient. Added mass and Basse history are usually small when that particle density is much bigger than the fluid. But when you have a flow that has strong acceleration, for example, a shock wave, you get strong acceleration between the phases. And now these unsteady terms become important, despite the fact that particles are much denser. And so now we have to unlike in incompressible gas solid flows, and for compressible gas solid flows, we have to be mindful that these terms now can have an order one effect. And so if we turn our attention to this quasi-steady drag force, this is one of the main unclosed terms appearing on the particle. It's well known the drag coefficient, how it scales with Reynolds number. So this is just, the classical scaling in the limit of zero Mach number. And as the Reynolds number increases, that drag coefficient decreases due to, the formation of boundary layer separation, eventually a turbulent wake that forms, right? So anyone who's opened up a Introduction to Fluid Mechanics textbook is very familiar with how this drag coefficient scales with Reynolds number. Now, when we talk about compressible flows, and if we hold the Reynolds number constant and increase the Mach number, it's a different story. So at fairly low Mach numbers, this is for an isolated particle, the drag coefficient's relatively insensitive to the Mach number until you get to this transonic region where you have the formation of a weak shock. And that's going to create a large pressure difference, which in turn leads to a ramp up in the drag coefficient. And eventually you get the formation of a bow shock. So these are really nice Schlerian images from Nagata. So this is experimental work from about 2 years ago that just shows what the density gradients look like, holding everything constant and just increasing the Mach number. And then eventually we have once the Mach number is high enough, it becomes insensitive. The drag coefficient is again insensitive to the Mach. So this blue line here is showing a correlation, a drag model by Singh et al. In 2022. There's a number of other drag laws that exist that show similar behavior by Loth and Henderson and others. But the main idea is we now have sufficient data to see how this drag coefficient scales. However, in the limit of a single particle. And so a focus of today's talk is going to be, what's this look like now when you have neighbor interactions, you have multi-particle effects on drag. I mentioned the unsteady term becomes important when you have strong acceleration. So this is showing a shock passing a particle. And just as the shock passes over the surface of the particle, you get a very strong pressure difference. And that leads to this huge ramp up in the drag coefficient. So this black line here showing the total force over the particle shortly after the shock passes over. And the quasi-steady drag is shown as this dashed line. So you can see very early times, this quasi-steady drag is actually it's a secondary effect. It's the unsteady contribution that's dominating until the shock passes over. And then the quasi-steady drag is the dominant force. And so at least at early times when a shock is interacting with the particle, the pressure gradient, added mass type of forces become very important. And so if we just put this together, this is just showing if we wanted to solve this set of equations, we have gas phase equations. So the volume filter Navier-Stokes. In this case, we can track individual particles in Lagrangian manner, or we could also extend this volume filtering and arrive at a set of two fluid equations. We're going to come back to this at the end of the talk. But the main idea is that if we want to solve a coarse-grained set of equations, the main unclosed terms are going to be the Reynolds stress or the pseudo-turbulence and drag. And that's going to be the focus of today's talk. All right, so now I want to sort of shift gears and go back to that that drag curve I showed here and provide some context on how we've arrived, what kind of data went into forming a drag correlation like this, what kind of work went into that, and what is the state of the art today. So to begin, if you're talking about the drag coefficient, probably the earliest correct statement of the fluid resistance or the drag force on a particle was in book 2 of Newton's Principia. So book 2 was Newton's work that really focused on fluid forces acting on bodies. And there's a nice quote here that says the resistance arising from the want of slipperiness in the parts of a fluid is, other things being equal, proportional to the velocity with which the parts of the fluid separate from one another. And so, you have to remember, this is 1687. This is centuries before we had a mathematical description of a proper mathematical description of fluid mechanics. This is before we had really a molecular perspective on fluids. And so this is probably the first correct statement. And it was this, book 2, where Newton introduced the idea of this drag coefficient. So essentially the force the fluid acts on a particle is proportional to the velocity squared, the area, the density, and this drag coefficient. And he showed through experimentation, at least at low speeds, that drag coefficient is about equal to 0.5. And so that was, it really set the groundwork for improving, this drag coefficient and looking at other regimes. Now, it was around this time that the British military became very interested in flow past the sphere because they were primarily using muskets, which use round shots, and cannon fire. And they were in a position where they wanted to start manufacturing large quantities of cannons and muskets over the next couple hundred years. And they put a lot of time and effort into really understanding the forces acting on these objects. So it was about 50 years later that a man of the name Benjamin Robbins, who's a British mathematician and a military engineer, who's really considered the father of of modern day what's considered gunnery. So he invented what's called the ballistic pendulum. The idea here is you fire, a cannon or a musket into this block, and that block is going to swing like a pendulum, and using energy arguments, so pretty simple, physics 1 type of energy arguments, you can estimate the momentum of the projectile. And if you know the mass of the object, you can then back out the velocity. And so this was introduced in this sort of principles of gunnery, which was translated into German by Leonhard Euler. So fun fact. And this is an image of an actual ballistic pendulum used for cannon fire. And what he showed was that if you have a bullet or, a small sphere traveling at Mach 1.5, the drag force he was predicting was 2 to 3 times what Newton, estimated 50 years prior. So he's showing that you have much higher drag coefficients. The challenge was with each shot, you only get one velocity measurement, and there was a lot of sort of variation, uncertainty from shot to shot. So there's a lot of error in this. But it gave, a clear view that at these high speeds, the drag coefficient was quite different. So that was 1742. About 100 years later, we arrive at Adams and Bashforth. And so remember at the beginning of the talk, I said, if anything else, by the end of this talk, you have a better idea of who these people were. So Cambridge has these comprehensive mathematical exams every year. And if you perform top in the class, you're considered senior wrangler. And if you're second highest scoring, you're a second wrangler. So folks, there are a lot of famous people who became senior wranglers. So Stokes was senior wrangler. Interestingly, I just learned that Maxwell was second wrangler. He was surprised. He assumed he was first wrangler, and he asked one of his servants to find out who was second wrangler, and came back and found out he was actually second wrangler. But there are a number of famous people. I think Newton was senior wrangler, but I can't remember if they were doing those exams at that time. But anyway, 1843, John Adams, I'd say Bashforth would have been senior wrangler, but Adams he basically scored the highest score there's ever been. It was outstanding. So he was senior wrangler, Bashforth was second wrangler, so they're classmates. 3 years later, John Adams goes on and discovers Neptune. So this is before there's any observational data for Neptune, using purely mathematics. He just using a team that discovered Neptune, which a couple years later was verified using through observation. So that's a pretty successful, just out of college career. The reason I'm speaking of Bashforth and Adams in the first place is because Bashforth went on 1864, worked for the British military, and invents the ballistic chronograph. So I'll talk a little bit more about this on the next slide. But the idea was he was able to get 10 velocity measurements per shot. And so this now opened the door to look at acceleration and accurately measure the acceleration of cannon fire and muskets. Essentially, what he invented was a very accurate stopwatch. So you can imagine you line up 10 sheets, and this musket ball or cannon will travel through these sheets, and then you get a time measurement every time it passes through. And now you can back out, the velocity acceleration information. And this is why Bashforth is considered really the father of modern day ballistics. But anyway, they end up teaming up some years later, 1883, and they're studying capillary action, and they develop a time integration method termed the Adams-Bashforth method. And so this is something that, at least in one of my codes, we still use today for as an extrapolation or a velocity prediction. We use Adams-Bashforth method, and I think it's used quite a bit in CFD today. But it was first sort of introduced in 1883 by these two college classmates. So that's who Adams and Bashforth were. So Bashforth has this now new technique. He can accurately measure, the acceleration velocity. And with that, he can estimate the drag coefficient. And what he shows, this is an actual plot from his one of his books. He shows at low Mach number, so this is drag coefficient versus Mach number. At low Mach number, or at least at moderate Mach numbers, you have this ramp up in drag coefficient where the force is proportional to the velocity cubed. And that's consistent with what Robbins showed with his measurements 100 years earlier. And then at much higher Mach numbers, there's this sort of level off, and the drag coefficient is now proportional to velocity squared, which is consistent with what Newton showed. And this instrument he developed, there was a committee formed to sort of verify the accuracy of it. And on that committee was George Stokes. And, this quote really says, it tells you everything you need to know about how Bashforth was looked upon by his peers. What Stokes says is, we do not think that any means existed before recording a number of successive small intervals of time with the degree of precision and trustworthiness attained by Professor Bashforth's instrument. So this was really hailed as a big success. It was even 100 years later still used in World War I. Interestingly, 100 years later, Miller and Bailey write a JFM paper in 1979 where they're compiling all the existing data on drag past the sphere at moderate Mach numbers. And what was interesting was shortly after Bashforth's measurement, the military switched to sort of cylindrical bullets. And so those are some of the last measurements of flow past spheres. And what they quote in that paper is that Bashforth's experiments scattered no more than modern day, data at that time. And if you look in Crow's multi-phase textbook, you can find a plot like this. And a lot of these curves are, using this these measurements, which I find quite interesting. And obviously, over the last couple of years, there's been, high-speed images and high-performance computing, and these measurements have been refined. This is sort of data that Eric Loth sort of compiled. I sort of replotted here, where this black line is showing the drag coefficient versus Reynolds number in the incompressible limit. So this is, Clifton Galvin, 1971. The red shaded here is what Loth calls the rarefaction dominated. So this is where we have non-continuum effects, rarefied effects, so finite Knudsen numbers. The yellow here is where you have what's called compression dominated. So you can see, compared to the incompressible limit, as the Mach number increases, that drag coefficient increases. And everywhere in green is what I estimate if you have, instead of flow past a single particle, but if you have multi-particle systems, what the drag force would be. And largely this is unknown, right? So if you have flow through a suspension of particles, you have wakes interacting with each other, the drag coefficient tends to increase with volume fraction. So somewhere in this green line, as long as we can assume the flow is continuum, we should have the drag coefficient should sort of exist up here. And so a large effort from our group was to develop new models in that region. So the next part of this talk, I want to show sort of some of our efforts in addressing this, these unknowns. So we've been, over the last couple of years, developing a high order, low dissipative flow solver. So it's based on pretty vanilla, high order, narrow stencil finite difference methods. It's uses what's called a summation by parts finite difference. So the stencil coefficients are modified near the boundaries, and this gives sort of a global energy estimate. So everything I'll be showing here is sixth order at the interior and third order at the boundary. We combine this with the SAT boundary treatment. So we treat the boundary conditions weakly. This gives us an energy stability. And then on top of that, we do convective splitting to get kinetic energy preservation. And then we combine that with a localized artificial diffusivity for shock capturing. So this allows us to get very localized shock capturing, high order methods to try to resolve turbulence and low dissipation. This is showing the drag coefficient over the sphere as a function of time, and we see very good match with existing experimental data. And we've combined all of this with a ghost point inverse boundary method. And so we have a paper in arXiv that shows how we combine all of these methods together and use it to study the drag force. So the flow setup, if you're familiar with what's traditionally been done over the last 20 years for developing drag laws, typically you consider a periodic box, you fill it with particles, you enforce a mean mass flow rate with like a mean pressure gradient type of force. And then you change the number of particles so you can systematically vary the volume fraction, you can systematically vary the Reynolds number. So we're doing that exact same thing. The difference here is we're doing this in a compressible setting. And so we can now also simultaneously vary the Mach number. So we're going to randomly distribute particles in a box. One thing to be mindful of is we want to make sure we're still in the continuum regime. And so for an ideal gas, we can relate the Knudsen number to the ratio of Mach number to Reynolds number. And what everything I'm showing here is done at a superficial Reynolds number of 300. So that's a Reynolds number where there's a volume fraction out front. So that using superficial velocity, we hold that at 300 so that at our highest Mach number, our Knudsen number is still small enough that we can, say that we're in the continuum regime. We're going to vary the Mach number from 0.1 to about 1.2 and the volume fraction from about 2% to 40%. And we use between 40 to 60 grid points across the diameter of each particle. So these are, fairly highly resolved simulations. And just to give you a sense qualitatively, this is showing Mach number 1.5, 2% concentration. The left, you can see the Q criterion. So the wakes are interacting. It's unsteady. So you have neighbor-neighbor interactions. The right, you're seeing contours of the dilatation. And so this is showing that you get these bow shocks that form in front of particles, and those bow shocks interact with each other. So this is, a very different sort of qualitatively very different than what you'd expect for incompressible flow. And just a little more, to compare this to what we'd expect at low Mach number, the top here is showing the velocity magnitude and the bottom is pressure. So at Mach 0.1, this is what you would see with like an incompressible solver at Reynolds number 300 and 10% concentration. This is just a 2D slice. So the flow is unsteady. You have wakes interacting with each other, and the pressure is fairly uniform. But as you increase the Mach number, you get these shocklets that form. So you get these shock waves that interact. And the pressure distribution is highly unsteady. And so we'd expect this should have a huge effect on the drag force, and likely in non-trivial sort of ways. So this is just showing, drag force normalized by Stokes drag versus volume fraction. The symbols are simulations at Mach 0.1, and all of the gray are existing correlations for incompressible flow. So we lie within sort of the incompressible, what's been reported for incompressible flow. Obviously there's this large variation, and that's sort of an ongoing discussion about what's it mean when you claim DNS and you have this much variation among different simulations. But still, we're pretty happy with the results that we're getting because it's lying within the incompressible limit. The right is showing drag versus Mach number. This green and pink here is what you'd get from existing single particle correlations. So the drag is fairly constant until you get to Mach about 0.8, and then you get this ramp up. And we see two main effects when you add multiple particles. One is as the volume fraction increases, the drag force increases. So the magnitude of the drag increases with volume fraction. But also that critical Mach number where you see that ramp up due to the emergence of shocks happens sooner and sooner. So you get lower critical Mach numbers as the volume fraction increases. So this suggests that for a given Mach number, as you increase the volume fraction, we're observing more and more compressibility effects, which is an interesting observation. This is a snapshot of one of the simulations. You can see that the flow tends to, even if it's subsonic, tends to accelerate between the particles. You get these shocklets that form. And so in the absence of any particles, this would just be uniform flow. And so clearly there's these enhanced compressibility effects due to the presence of particles. What I'm showing here is a turbulent Mach number. So this is the turbulent kinetic energy normalized by the mean sound speed. This is usually a proxy for level of compressibility. And at least at low Mach number, it increases slightly with volume fraction. But at higher Mach numbers, you see the turbulent Mach number increases quite a bit with volume fraction. And so again, this is suggesting this increase in compressibility as we increase the volume fraction. And so what we wanted to do is develop a drag model. And these, this is a high dimensional problem. That this drag coefficient is a function of Reynolds number, Mach number, volume fraction. And if you've ever looked at isolated drag coefficients as a function of Mach number for an isolated particle, they can be, very involved, have a lot of terms. And so we wanted really the simplest possible drag coefficient that captured these effects. So the idea was we were writing the drag coefficient as the drag coefficient for an isolated particle multiplied by a volume fraction correction. But we know through this observation that this critical Mach number, the compressibility changes with volume fraction. We're replacing the Mach number with a volume fraction dependent Mach number here. So here we're using a simple volume fraction correction by Singani. For an isolated particle, we're using a drag correlation by Singh et al. So we could have used a model by Henderson or Loth or other models. This seemed to be the least sensitive to the model coefficients. And so it splits this drag coefficient into sort of subsonic and supersonic. I'm not going to go into details here, but there's a 2022 paper that introduced a new drag correlation for a single particle. And we replaced the Mach number with this effective Mach number. And so this is inferred from the simulations. Essentially, as the volume fraction increases, the effective Mach numbers is increasing. And if we, test this correlation for Mach number 0.1 to 1.2, the symbols are data, the blues are correlation. Overall, we see a fairly good fit. One thing you can notice is as I increase the Mach number, we have less and less data at higher volume fractions, right? It turns out that running simulations at high volume fraction and high Mach number is numerically, it's extremely challenging. And what I'm going to argue in the next 5 minutes is I think also it's unlikely that in most practical settings, you'll have steady state flows at Mach greater than 1 through dense suspensions, because you need a ton of power to sustain a flow through those dense suspensions. But if we want to, really validate this at higher volume fractions and Mach numbers, we need more data. So in the last couple minutes, I just want to talk a little bit about what we've done with turbulence modeling. So like I said, drag was one of the main unclosed terms, but so is Reynolds stress. We're going to consider a planar shock interacting with a suspension of particles. The shock will pass through. There'll be a reflected shock and a transmitted shock, and then we'll have pseudo turbulence generated, the flow chokes, and all of that. And so this is just showing an example of one of the 3D calculations, 20% volume fraction. This is showing Schlerin on the top and the local Mach number on the bottom. And you can see, again, the flow goes through, there's lots of velocity fluctuations, and the flow chokes downstream and accelerates to supersonic speeds. So in order to look at this, we wanted to really properly, post-process and average these equations and really understand the mechanisms contributing to the transport of turbulence. So if we consider this, statistically 1D flow, we have the transport of turbulent kinetic energy. We have production due to mean gradients, so that would exist even for single phase flow. We have a turbulent transport term, a pressure strain term. So this is due to dilatation. So this will arise when the flow is compressible. Viscous dissipation, and then this P here, this is the production due to drag. So this is the main contribution of how particles are inducing turbulence. And if we look at the budget for this case, you can see that within the curtain, this is X, so everything shaded is in that particle curtain. We essentially have drag production balanced by viscous dissipation. Near the edge of the particle curtain, where you have volume fraction gradients, you have pressure strain playing a role, and you also have mean gradient production at the downstream edge. So we're starting to understand, what's contributing to the turbulence here. And in order to develop a model, we've been looking at sort of we started by looking at a one equation model. We wanted to transport the pseudo turbulence because we observe that we have this turbulent kinetic energy downstream away from particles, and existing models that account for pseudo turbulence, algebraic models, couldn't predict any finite TKE away from particles. So we wanted to come up with a one equation model. We have a mean gradient production that's closed. Drag production is closed if we have a drag model, and we lump everything else into sort of a dissipation. And so our initial attempt was to close this dissipation with an algebraic model that sort of switches on and off whether or not we're in the particles. And this is comparing the TKE for different cases and against 3D DNS that from Bala's group. And overall, it worked fairly well, but it's super sensitive to these coefficients we put out front. And so the work we're doing now is we're proposing a two equation model. We transport pseudo turbulence and its dissipation, where most of these terms are closed from single phase flow, but we have this time scale that sort of dictates how much of the energy gets produced and dissipated due to drag. And so right now, what we're working on is using particle resolved simulations to quantify this time scale, this dissipation time scale, to arrive at a two equation model that we can use in either a two fluid or an Euler-Lagrange type of model. Okay, so in the last 2 minutes, I just want to talk about, sort of putting this all together and kind of work we're currently doing in future directions. So if you remember at the beginning of the talk, I was saying this work's funded by NASA. They're interested in plume surface interactions. And so if we consider an underexpanded jet, so we have Mach 1 at the nozzle exit, impinging on a bed of particles. For the simulations I'm showing, this is going to be Earth ambient, just to begin. I'm going to consider 400 micron particles, and this is relevant for the Martian regolith. So the coefficient of restitution and coefficient of friction we've obtained from measurements from Martian regolith. But we're using an Euler-Lagrange method, so we're simulating each individual particle here. We're using an inverse boundary method, that ghost point inverse boundary method for the nozzle. And you can see some of the details on the simulation here. But essentially what we have is a compressible jet impinging on 40 plus million particles. And this is an example where we have the nozzle pressure ratio of 3.2. So you can see you get this Mach disk that forms. And this is just a 2D slice of the 3D simulation, but you can see this distinct cratering, this sort of W-shaped crater. The particles are being ejected at this angle, and you get this, what I like to, I think of this as sort of a Worthington jet, type of feature here that forms underneath that Mach disk. If we run the exact same simulation, but at a lower pressure ratio, you can see there's no mock disk that forms. You have these a series of mock diamonds, and unlike this W-shaped crater, you get this U-shaped crater. And so we were curious why, all we did was change the pressure ratio. Why was the crater morphology so distinctly different? And so this is very preliminary work, but essentially this is showing the pressure field for these two cases. And you can see when you have the formation of a mock disk, you have this low pressure region that forms and these high pressure regions that form out here that forces these particles up in the middle. Whereas when you don't have the emergence of a mock disk, you have high pressure in the axis of the jet that erodes the surface out. And so simply changing the pressure ratio, we get distinctly different crater, but also the ejecta, the angle the particles eject at is also distinctly different, which is quite interesting in my view. And if we take one of these simulations and we look at a joint PDF of Mach number and volume fraction, what we see is that we have very high probability of dense flow at low Mach. So that's this region 1, that's like deep inside the soil. And we have very high probability of high Mach at low concentration. So that's at this ejector region. And then in sort of this, where we have a lot of mixing and erosion, we have moderate Mach numbers and moderate volume fraction. So if you remember those plots of drag, we didn't have data out here, right? High volume fraction and high Mach number. But my argument is that it's unlikely in most practical applications you're going to have, quasi-steady state drag sustained under these conditions. You just need a crazy amount of power to force the flow at those high Mach numbers. But again, it's application specific. So this gives me a warm, fuzzy feeling, that we don't have to worry about running simulations in these very extremely difficult conditions where you have near closed packing at supersonic speeds, because at least in some of these flows, it's just a very rare event. So to conclude, I'd like to just say, compared to incompressible flow, compressible multi-phase flows are just far more complex, wider range of scales. These unsteady contributions to the forces become relevant. The two main unclosed terms that we need to really focus on modeling is this pseudo-turbulent Reynolds stress and drag. The modern day drag laws had this interesting sort of history from 18th century cannon firings. And, we've developed a new drag law. We're still refining it, at different Reynolds numbers, but it seems that compressibility effects increase as the volume fraction increases. And we're currently working on a 2-equation-like model for that pseudo-turbulence. Here are just some references for some of the work that, where this can be found. I'm working on an annual review paper on this topic that covers a lot of this material. So if you're interested in this work, keep your eye out for that. And a lot of this work was done in our in-house code. And if you're interested in running simulations of compressible multi-phase flow, Lagrangian particles, immersed boundaries, and so forth, visit this website, email me, and I'm happy to share the code itself. And with that, thank you for your attention, and I'm happy to take any questions there might be.
Very well done, Jesse. So the floor is open for questions. You're welcome to unmute yourself and ask your question. You can raise your hand. We'll monitor the chat as well. If you'd like to type your question in, I'd be happy to read it. But while people are thinking of questions, Jesse, I have at least one for you.
Sure.
Very interesting talk. I'm an experimentalist, so I don't do all the complex modeling, but I wonder how is this easily extendable to non-spherical particles? Because you can imagine particles in, say, Martian soil are not spheres; they're all potato-shaped or sharp-edged particles.
Yeah,
how would you extend this to non-spherical particles?
Yeah, so NASA had a program that was focused on plume surface interactions, and it was very clear they're very interested in non-spherical particles, right? So lunar regolith, Martian regolith are I wish I had a picture here. So on Mars, the surface of Mars, the atmosphere is about 1% of Earth ambient, which is low, but as far as planets go, it's considered quite high. And it's enough that you get sort of erosion due to Martian type of wind, and it's a high enough that incoming sort of meteors and stuff get broken up. So the soil or the regolith on Mars, it tends to be a lot more spherical than on the moon. The moon is very jagged. And I have a great picture somewhere that just shows an image taken from one of the landers of this it looked beautifully spherical particles on the surface of Mars, which I'm like, oh, that's great. But obviously, you know, in reality, there's a lot of places on Mars it's not very spherical. And my argument was that there's so much that we don't know in this regime for spheres that I was really pushing hard. We need to really get to the bottom of, you know, we didn't even know what the drag looked like for spheres, let alone non-spherical, right? So everything I showed here is really, let's start with spheres, build a framework. I imagine with non-spherical particles, we'll see a similar effect. The drag will increase with volume fraction, compressibility effects will happen sooner. You can imagine shocklets forming off of sharp edges of particles and so forth, right? So I think, you know, everything I've said here lends itself towards non-spherical, but what we need is good data. And there's work out of NASA Marshall and other places where they were doing experiments of supersonic jets impinging on particles of different shapes and trying to look at the erosion and cratering. So the erosion is very different if you have spheres versus non-spherical particles. So there's experiments being done, but those type of experiments, it's really difficult to, you know, it's opaque. It's very difficult. There's a lot of different techniques to try to, in non-intrusive ways, measure the crater shape and so forth, and the ejecta speed. So there's work being done, and it's important work. But yeah, I think you can imagine doing these particle resolve simulations for non-spherical particles as well. But again, this is just laying the groundwork to eventually look at those scenarios.
Okay, so Bala, before I get to you, I'm going to read one from the chat, if that's okay. Jesse Bruno Fraga writes in the chat that he can't unmute because he's commuting, but he said, great talk. My question is, did you observe a relevant influence on particle size on overall drag? And this is really for preserving the same volume fraction.
Yeah, that's a great question. So everything we did here, we held the superficial Reynolds number constant, and we varied the Mach number and volume fraction. So when I think of particle size, that plays a role on the Reynolds number, right? Because, you know, at least I like to think of things in terms of non-dimensional numbers. And so by changing the size, you change the Reynolds number. And so we're, you know, in my opinion, changing the size of Reynolds number would lead to, you know, probably a different form of this effective Mach number. And I'm currently collaborating with the group now that's looking at a different range of Reynolds numbers. And overall, we're seeing this drag correlation here works quite well across any of the available data outside this set of Reynolds numbers. So that's where I imagine size effects comes in. But there's been great work by Andreas Osnes, has a couple of PRF papers showing particle size effects in these during shock particle interactions. And so I mentioned that the unsteady contributions like added mass, when you have a shock wave, it doesn't scale with the density ratio, it scales with the particle size. So so these unsteady contributions will vary based on particle size. And so, you know, the particle diameter will play a big role here. But at least what I showed here in this work here was a fixed Reynolds number.
Okay, go ahead, Bala.
Hey, Jesse, great talk. I have two questions. The first is a technical question. How do you handle interparticle collisions in the final set of movies that you showed?
Sure. So in these calculations, we're using a saw sphere collision model. So it's just like, you know, it's basically CFD DEM. Now, one of the challenges is that, you know, in order to get this, the coefficient of restitution and the friction coefficient is set by the collision timescale. And so if you want to properly resolve the collisions, you have to resolve the collision timescale well. And what we find is because this is an explicit code, so we're resolving the gas phase acoustics, this acoustic CFL. And because our time step's small enough to resolve the acoustic CFL, we don't have to make our time step that much smaller to resolve the collision. So this is essentially a saw sphere collision model.
Okay. My second question is, in this case, what kind of drag law do you use? Because you showed a quasi-steady drag.
Yep.
But if you look at these particles, how quasi-steady the flow is, or if you look at from particles perspective, and
Yep,
as you go over, they seem to be probably rapidly changing their environment. And how do you handle that?
Yeah, so we have a strong collaboration with Ray Nee's group at Johns Hopkins, where we're doing, it's a different regime. It's a dilute regime of particles going through under expanded jet. So the particles are passing through Mach disks. And for that case, we've looked closely at the quasi-steady drag versus added mass and lift and so forth. And what we find is the quasi-steady drag still plays a very big role, even if the flow is accelerating. And using the Mach number correction is really important. So if I were to use like Gedaspo's drag, it would really give me something very different than if I had a combination of volume fraction and Mach number correction. But in those calculations, we were modeling, so we include the pressure gradient effect, or this undisturbed force on the particles. We modeled the quasi-steady drag with the drag correlation I showed here. With the viscous unsteady, we neglected, and then the inviscid unsteady or added mass, we used the Mach number corrected added mass coefficient that your group proposed. So we were using that here. We haven't systematically sort of looked at the relative role of each force in different parts of the flow for this case.
Okay. Thank you.
So Jesse, I have one more question for you. I think you just mentioned about before Bala's question that the effective drag is really particle size dependent. Is that correct?
Well, the particle size plays a role in the Reynolds number, right? So if you have if everything's constant, you change the size, you can change the Reynolds number. So that has an effect on the quasi-steady drag. But what I was alluding to was these if you were to take the ratio of, say, added mass to quasi-steady drag, right? So what's the relative importance of oh, sorry, I have that plot here, right? So what's the relative importance of, say, the unsteady part to the quasi-steady drag? Like, do I need to worry about it? Do I need to care about it? If this was an incompressible flow, my density ratio is 2000, I don't need to worry about added mass. I mean, it's just going to be negligible compared to quasi-steady drag. But scaling arguments, I think Bala has a nice JFM paper from like 2002 that shows when the gas is accelerating, it no longer scales like the density ratio, but it scales like a length scale in the fluid, which if you have a shock, that, you know, it's 1 over that length scale is very big, and the particle diameter. And so the relative effect of the unsteady forces on the particles, it does depend on the particle size. And so what this, you know, suggests is that if you were to do a shock particle interaction for, say, a polydispersed suspension of particles, you can imagine having shock-induced size segregation. So one of my students ran a bidispersed simulation of a shock interacting with 2 different size particles, and you get size segregation not only due to collisions, because this was fairly low concentration, but just because, you know, the unsteady contributions are different for the big versus small particles. So when you have a shock going through these particles, yeah, different size particles, you can get size segregation because of that.
That was my question. Thank you for answering it before I could ask it.
Yeah, there's so many, I mean, there's so many unanswered questions in this area. I think there's so much interesting work to be done. So I think this area is just, it's a very fun field to be working in, because like I said, you know, something as simple as what's the quasi-steady drag, you know, we're just starting to look at now, right? So a lot to be done.
So we're at the top of the hour. Are there any other questions for Jesse? Well, with that, Jesse, I want to